Imagine a dimly lit curing cellar. A high-tech sensor blinks with a steady, rhythmic light. It isn't plugged into a wall. It has no lithium battery. Instead, it draws its power directly from the chemical fermentation of the meat hanging beside it. This isn't science fiction. It's the logical next step of research already underway in Italy, where scientists have built the world's first fully edible battery from grocery store ingredients. Welcome to the Oddball Hall of Fame. This is an archive of engineering projects born not from the luxury of research grants, but from the raw, cold edge of desperation. Today, we peel back the layers of history to examine the Ice Giant, a 2,000-foot-long aircraft carrier made of frozen sawdust designed by the British to survive the U-boat-infested waters of the Atlantic. We will stand in the shadow of the chicken gun, a massive compressed air cannon that fires poultry at the speed of sound to simulate the violent physics of a bird strike. But beyond the initial shock of these inventions lies a deeper truth about how the human mind solves problems when the standard tools of civilization, steel, fuel, and conventional logic, begin to fail. Stay until the end to discover how a stretch of highway in the New Mexico desert uses the physics of sound to psychologically manipulate drivers into slowing down. We are looking for the point where the absurd meets the essential. Let's begin. Imagine a warship so vast that it is essentially a floating island. A ship that doesn't just resist torpedoes, but absorbs them, healing its own wounds with the freezing waters of the North Atlantic. In 1942, the British Admiralty wasn't looking for a miracle. They were looking for a way to stop the bleeding. They were losing hundreds of ships to German U-boats, and the steel needed to build an escort fleet simply did not exist. The solution was proposed by Geoffrey Pyke, an inventor known for ideas that sat on the razor's edge between madness and genius. He suggested building a ship out of Pykrete. To the naked eye, Pykrete looks like a muddy block of ice, but its molecular reality is far more complex. It is a composite material, 86% water and 14% wood pulp or sawdust. In material science, we know that ice is high in compressive strength, but incredibly low in toughness. It is brittle and shatters easily. However, when you introduce wood fibers, they act as a reinforcing matrix. These fibers distribute the energy of an impact, much like the carbon fibers in a modern supercar. A block of Pykrete could be hit with a hammer or even a bullet, and it wouldn't shatter. It behaved more like concrete than ice. To prove its strength, Lord Mountbatten famously brought 2 blocks to a high-level meeting attended by Winston Churchill and Franklin D. Roosevelt. He shot a block of regular ice with his pistol, and it shattered. When he shot the Pykrete, the bullet ricocheted off and reportedly grazed an admiral's leg. The room was convinced. The proposed vessel, Project Habakkuk 2, was a gargantuan undertaking. To understand its scale, let's compare it to ships you might know. The RMS Titanic, the most famous ship in history, was 882 feet long and displaced about 52,000 tons. Habakkuk was designed to be 2,000 feet long, more than twice the length of the Titanic. Now consider the icon of the seas, the largest cruise ship in the world today. Launched in 2024, it stretches 1,198 feet and weighs about 250,000 gross tons. It can carry nearly 10,000 people, passengers and crew combined, and is often described as a floating city. Habakkuk would have been 800 feet longer than even that. But the most staggering number is the weight. The final design called for a displacement of 2.2 million tons. That's more than 40 times heavier than the Titanic. Nearly 9 times heavier than today's largest cruise ship. The walls of this berg ship were designed to be 40 feet thick, solid frozen Pykrete, reinforced with an internal network of refrigeration pipes to keep the structure from softening. For comparison, the steel hull plates on a modern cruise ship are measured in millimeters, typically 25 to 40 millimeters thick. Habakkuk's walls would have been measured in stories. The weirdness of the ship was its greatest strength. It was a self-healing fortress. If a section of the hull was blown away by a torpedo, the crew could simply mix sawdust and water, pump it into the cavity, and let the ship's internal cooling system freeze the patch into place. The project reached the stage of a 1,000-ton prototype in the Canadian Rockies, which successfully survived a full summer without melting. However, the sheer engineering gravity of the project eventually brought it down. The amount of steel required for the internal refrigeration pipes was almost as much as building a traditional carrier. By 1943, longer-range aircraft and better radar had closed the mid-Atlantic gap that Habakkuk was meant to fill. The prototype was abandoned in Patricia Lake, Alberta. It took 3 hot summers for it to completely melt. Its remains still rest at the bottom of that lake today, marked by an underwater plaque, a haunting what-if of history. There is a specific, violent sound that occurs when a high-performance jet engine swallows a bird at 30,000 feet. It is the sound of precision engineering meeting biological mass at hundreds of miles per hour. To solve this, aerospace engineers built a weapon that seems like a piece of dark comedy: a 60-foot-long cannon that fires chickens. Since the 1950s, the chicken gun has been the gold standard for aviation safety. The science behind it is rooted in kinetic energy. The formula tells us that velocity is the most dangerous variable. A 4-pound bird hitting a windshield at 500 miles per hour carries the same energy as a small car being dropped from a 3-story building. Why use a real chicken? This is where physics gets interesting. A bird strike is a soft body impact. Unlike a metal hailstone, a bird behaves almost like a fluid upon impact. It flows across the surface, creating a shock pulse that travels through the material in ways a hard object cannot. To accurately test if a cockpit windshield will shatter, engineers need a projectile that mimics the density and viscosity of a real bird. The cannon itself is a marvel of compressed air engineering. It uses a high-pressure reservoir to release a wall of air that accelerates the poultry down the barrel. They use dead, supermarket-grade chickens, which are carefully weighed and brought to room temperature to ensure the fluid-like behavior is consistent. The Federal Aviation Administration requires birds to be at a natural consistency because a frozen bird acts like a solid rock. It doesn't deform on impact the way a real bird would in flight. There is a famous story, possibly apocryphal, about a team that borrowed a chicken gun but forgot to thaw their projectiles. The frozen chicken, behaving like a solid armor-piercing slug, reportedly went straight through the bird-proof glass, through the pilot's seat, and out the back of the test rig. The reply from NASA was simple: "Gentlemen, thaw your chickens." Whether that specific event is a legend or a literal fact, the scientific lesson is absolute. The difference between a soft body impact and a hard body impact is the difference between a safe landing and a disaster. Every time you board a commercial flight, your safety is predicated on the data gathered by these cannons. The chicken gun is a visceral, unsettling piece of engineering that proves sometimes the only way to test a high-tech machine is with a decidedly low-tech projectile. In 1780, an Italian physician named Luigi Galvani was dissecting a frog when something extraordinary happened. His assistant touched the frog's exposed nerve with a metal scalpel, and the legally dead amphibian's legs kicked violently, as if jolted back to life. Galvani believed he had discovered animal electricity, a vital force inherent to living tissue. He was half right. What he had actually stumbled upon was the chemical reaction that occurs when 2 different metals contact the salty fluids inside a body. The frog wasn't generating electricity. The frog was the battery. 240 years later, scientists in Italy have taken Galvani's accidental discovery and created something that sounds even more absurd: a fully edible, rechargeable battery made from ingredients you could find at a grocery store. Welcome to the strangest cooking show you've ever seen. Today's recipe: electricity. Let's go over the ingredients. For the anode, that's the part of the battery that gives up electrons, we're going to need riboflavin. You might know it as vitamin B2. Where do you find it? Almonds. That's right. The same nutrient that gives almonds their health benefits is also capable of storing and releasing electrons. For the cathode, the part that accepts electrons, we're using quercetin. This is a flavonoid, a type of plant pigment found in capers and red onions. If you've ever bitten into a caper and tasted that sharp, tangy bite, that's the same molecule that's about to power a circuit. Now, here's where it gets interesting. We need something to help the electrons move. For that, we turn to activated charcoal. And I need to be very clear, this is not the charcoal from your backyard barbecue. Regular charcoal briquettes contain binders, fillers, and sometimes lighter fluid, materials that would be toxic if consumed. Activated charcoal is different. It starts as regular charcoal, often made from coconut shells or bamboo, but then it's heated to extreme temperatures in the presence of steam or argon gas. This process burns tiny microscopic tunnels into the carbon, giving it a surface area of up to 3,000 square meters per gram. For reference, a single gram of activated charcoal has the internal surface area of roughly half a football field. This massive internal structure is what allows it to conduct electrons so efficiently, and it's also what makes it safe to eat. It's used in hospitals to treat poisoning and is sold as an over-the-counter supplement. Next, we need a separator, something to prevent a short circuit. In a traditional lithium battery, this is a synthetic polymer. In our edible battery, it's nori seaweed, the same kind wrapped around your sushi roll. The researchers soak the nori in a water-based electrolyte made from sodium hydrogen sulfate, an edible salt. Finally, we need something to collect the current. For that, the Italian team at the Istituto Italiano di Tecnologia borrowed a trick from pastry chefs: edible gold leaf. The same delicate foil used to decorate fancy desserts is thin enough and conductive enough to serve as the battery's terminals. And to hold it all together? Beeswax. The natural wax from honeycombs encapsulates the electrodes, protecting them from the acidic environment of the stomach. So let's recap the recipe. Almonds, capers, activated charcoal, seaweed, gold leaf, beeswax. This isn't science fiction. It's a peer-reviewed paper published in Advanced Materials in 2023, and it was named one of Time magazine's 200 Best Inventions of the Year. The prototype battery operates at 0.65 volts, a voltage low enough to be completely safe inside the human body, and can sustain a current of 48 microamps for about 12 minutes.
Our battery allows us to ingest, for example, a sensor, a sensing system, and degrade it into our body, like food, after it has performed its function.
That's not much, but it's enough to power small sensors, low-power LEDs, or the kind of smart pill that could monitor your gut health and transmit data to your doctor. And here is where the story comes full circle. The process of curing meat, like salami, is essentially a controlled fermentation. Lactic acid bacteria break down sugars, and this process involves a transfer of electrons. The same fundamental chemistry that powers your body, that made Galvani's frog kick, and that now powers this edible battery. Now, to be clear, the researchers at IIT did not use salami in their experiments. Their battery is entirely plant-based: almonds, capers, and seaweed. But the underlying biochemistry suggests an intriguing possibility. What if you could power a sensor using the fermentation energy of the meat itself? We're not claiming this is proven science. We're suggesting that perhaps, someday, a future scientist, maybe one of you watching right now, could explore this idea. With proper supervision at a university or research facility, of course. Please don't try to build a battery out of your lunch meat at home. But in a controlled lab environment? Who knows? The next chapter of edible electronics might be waiting in a deli case. From a frog leg twitching in 1780 to a battery made of almonds and capers in 2023, Galvani would be proud. Can a highway manipulate your brain into obeying the speed limit? In the New Mexico desert, on a fading stretch of the legendary Route 66, there's a quarter-mile of asphalt that will sing to you, but only if you follow the rules. In October 2014, near the small town of Tijeras, just east of Albuquerque, the New Mexico Department of Transportation partnered with the National Geographic Channel to build one of the strangest speed control devices ever conceived: a musical highway. The premise was simple. Most rumble strips are designed to jolt drivers awake with an ugly, grating vibration. But what if, instead of a warning, you offered a reward? The engineering behind the project is rooted in the physics of sound. Sound is created by vibrations. If something vibrates 330 times per second, it produces the musical note E. If your car's tires are rolling over a surface with grooves spaced exactly 2.4 inches apart, and you're traveling at exactly 45 miles per hour, the tires will hit those grooves 330 times per second. The result? An E note humming through the chassis of your car. By varying the spacing of the grooves, some closer together, some farther apart, audio engineers designed a rumble strip that plays actual musical notes. On this stretch of Route 66, the song is "America the Beautiful." The grooves were pressed into hot asphalt just inside the white line marking the edge of the road. If you align your right tires with the rumble strip and maintain exactly 45 miles per hour, the posted speed limit, the vibrations travel through your tires, into the frame of your car, and into the cabin as a recognizable melody. But here's the genius of the design. If you drive too fast, the song shifts into a higher, frantic key. The melody becomes dissonant, compressed, almost grating. If you drive too slow, the song drags into a low, distorted mumble. Only at exactly 45 miles per hour does the tune sound correct. This is acoustic psychology. The human brain craves harmony. When we hear music that sounds off, we feel an instinctive discomfort, a subtle but persistent urge to fix it. Instead of threatening drivers with a fine, the engineers created an environment where the driver wants to comply with the law simply to satisfy their brain's need for musical resolution. It's a quiet, intelligent form of social engineering. No police officer required. The musical highway was a hit. Drivers made U-turns just to hear the song again. Tourists from around the world detoured off Interstate 40 to experience the novelty of a singing road. But maintaining acoustic asphalt is expensive. Over time, the grooves wore down. New asphalt was laid over portions of the strip. By 2020, the official signs had been removed, and a spokesperson for the New Mexico Department of Transportation said simply, "There are no plans to restore the musical highway. The cost is outrageous."
He always said, we'd provide the road, but we would not spend any money, taxpayers' money, on this project because it was an experiment by National Geographic.
And yet, the road is still there. As of 2025, visitors report that portions of the melody can still be heard if you know where to look, and if you drive at exactly 45 miles per hour. Hand-painted signs have appeared, made by locals who refuse to let the attraction die. White paint marks the starting point. The musical highway may be fading, but its legacy is spreading. In 2026, 8 new musical roads are being installed along Route 66 to celebrate the highway's 100th anniversary. In India, a stretch of the Mumbai Coastal Road now plays the Oscar-winning song Jai Ho. In Japan, there are over 30 musical highways. The Singing Road of Tijeras proved that a boring safety feature can become a national attraction. And that is the spirit of the Oddball Hall of Fame, taking the mundane and making it sing. The Oddball Hall of Fame is more than just a collection of weird science. It is a testament to the fact that professional solutions are not always the best ones. From a 2,000-foot ice carrier made of frozen sawdust, to a cannon that fires chickens to prove a windshield is safe, to a battery made of almonds and capers, to a highway that plays "America the Beautiful." These projects remind us that engineering is, at its heart, the art of the possible. When you strip away the sleek glass and the polished steel, You are left with the raw human urge to solve a problem by any means necessary. The next time you're faced with a problem that seems impossible, look at the objects around you. Don't see them for what they are, see them for the physics they contain. A salami is a fermentation reactor. A highway is a musical instrument. A block of frozen sawdust is a warship. Because in the world of engineering, the only truly weird idea is the one that doesn't work. Thank you for joining us in the Hall of Fame. We'll see you in the next chapter of The Unknown. Now, here's the thing. The Oddball Hall of Fame has many more exhibits we didn't have time to cover today. We're already working on part 2, but we want to hear from you. Do you know of a strange invention, a desperate solution, or a piece of weird science that actually worked? Drop it in the comments. If it's wild enough, it might just make it into the next episode. Subscribe so you don't miss it.